Tonight, we need to talk about something that most people have completely wrong. When we think about the solar system, we imagine something almost cozy. A bright sun in the center, planets gliding in calm, predictable circles, everything humming along in peaceful order. Diagrams show clean orbits, evenly spaced, everything neatly labeled. What those diagrams never tell you is that the calm we see today is what's left after billions of years of bombardment. Stripped atmospheres and orbital chaos that once had the inner solar system looking nothing like it does today. The solar system is one of the most violent, hostile, and extreme environments you could imagine, and we are living right in the middle of it. And by the end of tonight, you will never look at that diagram the same way again. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The first thing you need to understand is the scale. Because almost everything terrifying about the solar system begins with distance. The solar system is not a small, closely packed neighborhood of planets. It is an almost incomprehensibly vast expanse of emptiness, punctuated by objects that range from quietly lethal to catastrophically violent. Start with the inner solar system. The Sun sits at the center, and 8 planets orbit at various distances. Mercury orbits at roughly 36 million miles from the Sun. Venus at about 67 million miles. Earth at 93 million miles. Mars at around 142 million miles. These are the 4 rocky planets, the ones we think of as the inner solar system. And yet, even within this relatively compact neighborhood, the distances are staggering. The gap between Earth and Mars at their farthest point from each other is over 250 million miles. That is a journey no human has ever attempted. We have sent robotic spacecraft, and the fastest of them have taken roughly 6 to 9 months to cross that void. But the inner solar system is not where the real scale reveals itself. It's when you move outward. Jupiter orbits at about 484 million miles from the Sun, Saturn at roughly 886 million miles. Uranus at about 1,780 million miles. Neptune, the outermost planet, sits roughly 2,790 million miles from the Sun. If you laid that distance out and tried to drive it at highway speed, 70 miles per hour, without stopping, it would take you over 4,500 years to reach Neptune from the Sun. And Neptune is not the edge. Beyond Neptune, the solar system continues for another enormous stretch. The Kuiper Belt extends from roughly 30 astronomical units out to 50 astronomical units. 1 astronomical unit is the distance from Earth to the Sun, 93 million miles. So the Kuiper Belt stretches from about 2,790 million miles to 4,650 million miles from the Sun. And beyond even that, the Oort cloud, a vast, spherical shell of icy objects beginning at roughly 2,000 astronomical units from the Sun, and potentially extending all the way out to 100,000 astronomical units. That outer boundary sits roughly 9,300,000,000 miles from the Sun, and the Oort cloud is considered part of our solar system. Our neighborhood, our home. Something that vast, that empty, that dark and cold is what we are actually living inside. When you absorb that scale properly, the comfortable school diagram starts to dissolve. And what replaces it is something more honest. Something harder to look at, without a certain quiet unease. The solar system diagrams you grew up with were drawn that way out of necessity. If you drew the solar system to true scale, with the sun as a circle 1 inch across, the Earth would be a dot smaller than a period on this page, sitting at a distance of about 9 feet from the sun. And Neptune would be a tiny speck, roughly 270 feet away. The Oort cloud, at true scale, would extend for miles in every direction from the center of your diagram. The visualization tools we use to understand our neighborhood systematically and unavoidably mislead us about what that neighborhood actually is. What it actually is mostly nothing. Vacuum, darkness, cold that approaches absolute zero, with occasional islands of matter scattered through the emptiness. Some of those islands are enormous, some are ancient, and some are dangerous. None of them are where the diagrams suggest they are relative to each other. In the true solar system, everything is impossibly far from everything else. Even the planets, which seem so close when drawn on a chart, are separated by distances that would take years to cross at the speeds of our fastest spacecraft. The distances are not the backdrop to the story of the solar system. They are the story. And those distances are full, not empty. Full of radiation, charged particles, magnetic fields, gravitational influence, and billions of objects we have only begun to catalogue. The sun itself is where the terror begins, because the sun is not the gentle golden lamp of popular imagination. The sun is a thermonuclear explosion that has been running continuously for 4.6 billion years. At its core, temperatures reach roughly 27 million degrees Fahrenheit, about 15 million degrees Celsius. The pressure at the core is 340 billion times greater than the atmospheric pressure we experience at sea level on Earth. Under those conditions, hydrogen nuclei fuse together into helium, releasing enormous quantities of energy in the process. The sun converts roughly 600 million tons of hydrogen into helium every single second. Every second. That energy radiates outward through the sun's interior, a journey that takes anywhere from 10,000 to 170,000 years just to travel from the core to the surface. A single photon of light born in the solar core bounces around in the radiation zone for what could be 100,000 years before finally breaking free at the surface and shooting out into space. 8 minutes later, it reaches Earth. The surface of the sun, called the photosphere, burns at roughly 10,000 degrees Fahrenheit, about 5,500 degrees Celsius. That is the cool part. The sun's outer atmosphere, the corona, reaches temperatures of 1 to 3 million degrees Celsius, roughly 1.8 to 5.4 million degrees Fahrenheit. Nobody fully understands why the corona is so much hotter than the surface beneath it. It is a mystery that has puzzled solar physicists for decades. One leading hypothesis involves the energy carried by magnetic waves, called outweighs waves, that propagate through the corona from below. Another involves small explosive events called nanoflares, which individually release relatively modest energy but collectively heat the corona to extraordinary temperatures. The leading hypothesis shifts depending on who you ask and what the latest observations show. But the heat is real, and its consequences reach across the entire solar system. The solar wind is the sun's atmosphere escaping into space continuously. Charged particles, mostly protons and electrons, flow outward from the corona in all directions at speeds ranging from roughly 250 miles per second to nearly 550 miles per second. These are not particles drifting gently outward. They are a constant, energetic stream of material, blasting through the entire solar system at all times. The solar wind sweeps past Earth, past Mars, past Jupiter and Saturn, past Uranus and Neptune, and continues outward for billions of miles until it finally loses the battle against interstellar space. The boundary where the solar wind becomes too weak to push back against the interstellar medium is called the heliopause. Voyager 1 crossed it in 2012, roughly 11 billion miles from the Sun. That is how far the Sun's direct physical influence extends. 11 billion miles of solar wind. Everything inside that boundary feels the Sun's breath on it, constantly, without interruption. The solar wind is not uniform. It varies in speed and density, forming structures and patterns as it flows outward. High-speed streams from regions of the solar corona, called coronal holes, overtake slower solar wind, creating what are called corrotating interaction regions. These are compressed zones of enhanced solar wind material that travel outward with the rotation of the Sun. When they reach Earth, they can trigger moderate geomagnetic disturbances. They happen all the time. They are routine features of the solar wind environment. But the solar wind is only the beginning of what the Sun does to this solar system. The Sun also produces coronal mass ejections, enormous eruptions of magnetized plasma ripped free from the solar surface and launched into space. A single, large coronal mass ejection can expel several billion tons of plasma. The cloud of material travels at speeds between roughly 90 miles per second and over 500 miles per second. When one of these clouds hits Earth, it interacts with our magnetic field and can cause geomagnetic storms. In mild cases, those storms produce the aurora borealis. In severe cases, they can damage satellites, disrupt GPS systems, create problems for airline navigation, and knock out power grids. The Carrington event of 1859 was the most powerful geomagnetic storm ever recorded. It was caused by a coronal mass ejection of extraordinary size. The storm induced currents in telegraph systems across North America and Europe so powerful that telegraph operators reported sparks flying from their equipment. Some lines reportedly continued transmitting even after being disconnected from their power sources, running entirely on geomagnetically induced current. The aurora was seen as far south as the Caribbean, Hawaii, and Colombia, close to the equator. If a Carrington-scale event struck today, the effects on our technology-dependent civilization would be severe. A study by Lloyd's of London estimated that a repeat event could cause economic losses in the United States alone of up to $2.6 trillion. And these events happen. They are not theoretical. They are a regular feature of the Sun's behavior. Weaker versions occur constantly. A truly powerful one is, in the assessment of solar scientists, simply a matter of time. The Sun also periodically releases solar flares, intense bursts of radiation that travel at or near light speed. A major solar flare can release as much energy as 1 billion hydrogen bombs in a matter of minutes. The X-ray and ultraviolet radiation from a large flare can reach Earth in about 8 minutes. It ionizes the upper atmosphere, disrupting radio communications, affecting GPS accuracy, and in extreme cases can present a radiation hazard to astronauts in space or to passengers on high-altitude aircraft flying polar routes. Solar flares are classified by their peak X-ray output. The largest recorded flare, which occurred in 2003 and was measured by instruments near saturation, has been estimated at class X45. To give that some meaning, the classification scale runs from class A, at the quiet end, to class X, at the energetic end, and within the X class, the numbers go higher with stronger events. An X-45 flare is roughly 25 times more energetic than the largest flare typically considered in hazard assessments. Its effects were mitigated only because the solar active region that produced it happened to be rotating away from Earth at the time. Had it been facing directly at us, the consequences for radio communications, satellite operations, and human spaceflight would have been substantially worse. All of this is coming from our star, the one we think of as warm and life-giving. And in one sense, it is. Life on Earth exists because of the sun's energy. But the same object generating that life-sustaining light is also a continuously active source of radiation, particle bombardment, and energetic eruptions that would be instantly lethal to any unprotected human being. The comfortable distance of 93 million miles, combined with Earth's magnetic field and atmosphere, is what keeps us alive. Without any one of those protections, the story of life on Earth would be very different. The sun's activity is not constant. It follows an 11-year cycle, oscillating between solar minimum, when activity is low and the sun's surface is relatively quiet, and solar maximum, when the number of sunspots, flares, and coronal mass ejections increases substantially. During solar maximum, the frequency and intensity of geomagnetic storms rises. The risk to satellites, astronauts, and power infrastructure increases. The sun reached solar maximum in the cycle that peaked around 2024, one of the more active cycles in recent memory. Several major coronal mass ejections reached Earth during this period, producing auroras visible at unusually low latitudes. No major infrastructure damage occurred. But scientists who study space weather were watching carefully. The margin between a spectacular aurora and a disabling geomagnetic storm can be surprisingly small. It depends on the orientation of the magnetic field embedded in the coronal mass ejection when it reaches Earth. If the field is oriented in a way that reconnects unfavorably with Earth's own field, the transfer of energy into the magnetosphere is maximized. That is when the damage happens. We cannot predict that orientation reliably until the cloud is already most of the way here, which means our warning time for the worst-case scenario is measured in minutes to hours. Not weeks, not days, hours. The sun generates an enormous magnetic field that is carried outward by the solar wind. This field, called the interplanetary magnetic field, or the Parker spiral, fills the entire heliosphere. It does not extend out straight from the sun. Because the sun rotates, approximately once every 25 to 35 days, depending on latitude, the field lines are wound into a spiral pattern, like water spraying from a rotating sprinkler. This spiral structure extends all the way out to the heliopause, organizing the charged particle environment of the inner solar system into a complex, structured electromagnetic environment. Earth's magnetic field interacts with this larger structure constantly. When the interplanetary magnetic field points in a particular direction, it can link up with Earth's magnetic field in a process called magnetic reconnection. When this happens, energy is transferred directly into Earth's magnetosphere, driving geomagnetic storms. These storms can disrupt satellite operations, interfere with GPS signals, create unexpected currents in long electrical conductors like power transmission lines and pipelines, and expose people at high altitudes, particularly airline passengers and crew on polar routes, to elevated radiation doses. In most cases, the effects are manageable. A satellite goes offline temporarily. A GPS reading is slightly off. Unusual readings in a pipeline monitoring system. But the interplanetary magnetic field does not always interact gently with Earth's field. The Sun's magnetic field flips at the peak of each solar cycle, and during that transition, the field becomes more complex and tangled, with multiple poles appearing simultaneously. During these periods of peak solar activity, the frequency of solar flares and coronal mass ejections increases significantly. And we have built a technological civilization whose most critical infrastructure is vulnerable to the consequences. The Sun is also changing over geological time. Stars of the Sun's type gradually increase in luminosity as they age. The Sun is estimated to be roughly 30% brighter today than it was when the Earth first formed. Billions of years ago, a fainter Sun should have meant a colder Earth. Cold enough that liquid water should not have been able to exist on the surface. But the geological record shows liquid water has been present on Earth for nearly 4 billion years. The resolution to this apparent contradiction, called the faint young sun paradox, involves higher concentrations of greenhouse gases in the early atmosphere, possibly supplemented by other factors not yet fully understood. The point is this: the Sun's output is not fixed. It changes. On human timescales, the change is imperceptible. But on geological timescales, the Sun has already become dramatically more luminous than it was, and it will continue. In roughly 1 billion years, the Sun will be bright enough that Earth's oceans will begin to evaporate. The water cycle will break down. Earth will enter a runaway greenhouse phase, similar to what Venus experienced much earlier in its history. The surface will become uninhabitable. That is not tonight's emergency. But it is a reminder that the star warming us is not a fixed and permanent friend. It is a slowly evolving object with its own timeline. And we exist at a particular, transient moment within that timeline. With that picture of the Sun in mind, we can begin the journey outward. Mercury, Venus, and Mars tell 3 different stories about what can happen to an inner planet. Mercury today has essentially no atmosphere. What remained was stripped away over time by the solar wind. Without an atmosphere, there is no protection from solar radiation. Temperatures swing from roughly -270 degrees Fahrenheit at night, around -168 degrees Celsius, to over 800 degrees Fahrenheit on the sunlit side, which is roughly 427 degrees Celsius. Mercury is geologically nearly dead. Its surface preserves craters going back billions of years. No plate tectonics, no volcanic resurfacing, just the accumulated record of every impact it has survived. Venus, at first glance, seems like it should be similar to Earth. It is almost the same size, almost the same mass, and orbits at a distance from the Sun, not dramatically different. But Venus is a vision of what a runaway greenhouse effect looks like in practice. Its atmosphere is 96% carbon dioxide, with clouds of sulfuric acid. The atmospheric pressure at the surface is roughly 92 times Earth's surface pressure. That is equivalent to the pressure you would experience at about 3,000 feet underwater. The surface temperature of Venus is roughly 860 degrees Fahrenheit, about 460 degrees Celsius. Hotter than Mercury, even though Venus is farther from the Sun. The thick atmosphere traps heat with extraordinary efficiency. The surface is hot enough to melt lead. The Soviet Venera probes that successfully landed on Venus in the 1970s and early 1980s returned data and images before being destroyed by the environment. The longest surviving lander, Venera 13, lasted 127 minutes before the heat and pressure ended the mission. 127 minutes. That is how long our best hardware of that era could survive on the surface of our nearest planetary neighbor. Venus rotates so slowly and in the opposite direction from most planets that a Venusian day is longer than a Venusian year. Earth and Venus are twins that took radically different paths. One has oceans, mild temperatures, and life. The other has sulfuric acid clouds, crushing pressure, and temperatures that destroy metal. The line between those two outcomes was not obvious from the start. It was the result of specific conditions, specific processes, and specific timing. Earth is the third planet, and understanding it means understanding why it survived what Mercury and Venus could not. Earth's magnetic field, which shields the surface from the solar wind, is generated by convection in the liquid outer core. That convection is driven by heat from the inner core and by the composition of the iron-nickel alloy. The magnetic field is not perfectly stable. It flips periodically. Over geological time, the north and south magnetic poles swap. This has happened hundreds of times in Earth's history. During a reversal, the field does not simply rotate. It weakens, becomes disorganized, and can temporarily drop to a fraction of its normal strength. The last full reversal occurred roughly 780,000 years ago. During a reversal, the weakened field would provide less protection against the solar wind. Cosmic ray flux at the surface could increase. The South Atlantic anomaly, a region of the southern hemisphere where the magnetic field is unusually weak today, has been interpreted by some researchers as a possible early sign of such a process. The mechanism is real. The shield is not permanent. And then there is the Moon. Earth's moon is the most studied extraterrestrial body in human history. We have walked on it. We have driven on it. We have drilled into it and brought samples home. The moon's surface, preserved without weather or erosion, records every major event in the early solar system. The Maria, the dark flat plains visible on the moon's face, were formed when enormous impacts punched through the crust and allowed lava to flood the resulting basins. These events were so large that the impacts created holes hundreds of miles across. The South Pole Aitken Basin, on the moon's far side, is one of the largest confirmed impact craters in the solar system. It is roughly 1,600 miles across and about 5 miles deep. Earth was hit too. Earth is a larger target with stronger gravity. During the late heavy bombardment, Earth absorbed at least as many large impactors as the Moon. Probably more. The geological evidence has been erased by plate tectonics, erosion, and volcanism. But the geochemistry of ancient rocks preserves the signature. Platinum group elements, which are rare in Earth's crust but abundant in many asteroid types, are found in higher concentrations in ancient rocks from this period. Those elements were delivered by asteroids. Billions of tons of asteroid material were incorporated into Earth during the bombardment. And the Moon itself, if current theories are correct, is the product of an impact even more extreme than anything during the late heavy bombardment. The giant impact hypothesis holds that early in the solar system's history, roughly 4.5 billion years ago, Earth was struck by a Mars-sized body. This impactor, which researchers have named Theia, hit Earth at a relatively shallow angle with a glancing blow. The energy released was extraordinary. Material from both the impactor and Earth's outer layers was vaporized and blasted into orbit. That debris eventually coalesced into the Moon. Earth and the Moon are, in this sense, the remnants of a catastrophic collision. The Moon is not a pristine world. It is the debris from one of the most violent events in Earth's history. And the Moon's presence has shaped everything that followed. The Moon stabilizes Earth's axial tilt. Without it, models suggest the tilt would vary chaotically over millions of years, between perhaps 0 degrees and over 85 degrees. The climate consequences of such variation would be severe. Seasons would become extreme. Ice ages would be harsher and more frequent. The stability of Earth's climate over the past several hundred million years, the stability that allowed complex life to evolve and persist, owes something to the presence of a large moon. A moon formed in violence. Held in place by the gravity of the same planet, it nearly destroyed at its formation. Mars tells a third story. Mars has a thin atmosphere, roughly 1% the density of Earth's. Its surface is cold, averaging about -80 degrees Fahrenheit, roughly -62 degrees Celsius. Liquid water cannot exist stably on its surface under current conditions. But the surface of Mars is covered in features that could only have been formed by liquid water. Valley networks, ancient lake beds, sedimentary layers, minerals that only form in the presence of water. Mars once had a thicker atmosphere and liquid water on its surface. What happened is that Mars lost its magnetic field. The interior cooled and solidified, ending the dynamo that had generated a global magnetic field. Without that magnetic field, the solar wind stripped away the atmosphere. Over billions of years, most of the Martian atmosphere was lost to space. The water followed. Mars became the cold, thin-aired desert it is now, because the solar wind, patient and relentless, took billions of years to accomplish what no single dramatic event could. The lesson of Venus and Mars is the same. The conditions that make Earth hospitable are not inevitable. They are not permanent. They result from a specific and unusual combination of factors. The right distance from the Sun. A magnetic field generated by a convecting iron core. A large moon stabilizing the axial tilt. Plate tectonics cycling carbon through the atmosphere and oceans to regulate temperature. An active hydrological cycle. Remove any one of these things and the outcome might look like Venus, or Mars, or something worse. Mars also has 2 moons, and they are among the strangest objects in the inner solar system. Phobos, the larger of the 2 Martian moons, orbits Mars at a distance of only about 3,700 miles. That is closer to the surface of Mars than any other known moon is to its parent planet. Phobos orbits so close and so fast that it completes an orbit in just 7 hours and 39 minutes. Mars rotates once every 24 hours and 37 minutes. So Phobos rises in the west and sets in the east, multiple times each Martian day. Phobos is also spiraling inward. Tidal forces from Mars are slowing its orbit, causing it to descend toward the surface. In roughly 50 million years, Phobos will either impact Mars or be torn apart by tidal forces into a ring of debris surrounding the planet. Mars, which today has no ring system, will eventually have one, created by the destruction of its own moon. Deimos, the smaller Martian moon, is slowly spiraling away from Mars. Eventually, Deimos will escape Mars entirely. The 2 moons of Mars will ultimately go in opposite directions. one falling in, one drifting away. Now look at those 4 inner planets and what they have in common. Every one of them is scarred. Mercury is covered in craters. The Moon records billions of years of bombardment. Mars is pocked with ancient impacts. Even Earth, where geological processes erase most of the evidence, carries the chemical fingerprints of what happened. There is a reason for this. And it tells you something important about how this solar system came to be the way it is. Astronomers call this period the Late Heavy Bombardment. It is the period, beginning roughly 4 billion years ago, when the inner solar system was absolutely battered by an extraordinary number of large impacts. The evidence is written on every airless world we have studied. The Moon's surface is covered with craters, most of them ancient, formed during this period. The oldest surfaces of Mars are cratered at the same density. Mercury, which has almost no geological activity to erase old features, is essentially a museum of impact history. Even on Venus and Earth, where erosion, volcanism, and plate tectonics have erased most ancient craters, geochemical signatures in the rock record preserve traces of the bombardment. The leading explanation for why this bombardment was so intense involves the migration of the giant planets. In the first hundreds of millions of years after the solar system formed, the orbits of Jupiter, Saturn, Uranus, and Neptune were different from where they are today. The gravitational interactions among the 4 giant planets were unstable over long timescales. Computer simulations, most notably those described in the Nice model, a set of solar system formation models developed primarily by scientists at the Côte d'Azur Observatory in France, show that around 4 billion years ago, these interactions led to a period of chaotic orbital rearrangement. Jupiter and Saturn fell into a resonance with each other, their orbital periods aligning in a simple ratio that amplified their gravitational influence on the smaller bodies around them. The result was catastrophic for the outer solar system. Ice giants were scattered inward and outward. The disk of icy material beyond the planets was violently disrupted. Billions of comets and large rocky bodies were flung toward the inner solar system. What followed was a sustained barrage lasting hundreds of millions of years. Craters, hundreds of miles across, were gouged into the surfaces of Mercury and the Moon. Impacts on Earth during this period may have temporarily boiled the oceans, not warmed them, boiled them. The energy deposited by the largest impacts was sufficient to vaporize bodies of water and sterilize the surface. Any life that had begun during this period would have faced repeated existential threats. Whether life survived these events, sheltered perhaps in deep ocean vents or subsurface rocks, is a question that remains genuinely open. What is certain is that the inner solar system was not a peaceful place. It was a shooting gallery. And the reason it eventually settled into the relative calm we see today is not because the solar system became inherently stable. It is because most of the projectiles were used up. The supply of large impactors dwindled over hundreds of millions of years as they collided with planets, fell into the sun, or were ejected from the solar system entirely. But the supply was not exhausted. There are still billions of objects in the outer solar system capable of being redirected toward the inner planets. The bombardment slowed. It did not stop. There is something important to understand about orbital resonance here, because it is the hidden mechanism behind much of the solar system's most dramatic history. When 2 bodies in orbit around the same central object have orbital periods that fall into a simple ratio, they repeatedly experience each other's gravitational pull at the same point in their orbits. This reinforcement can either stabilize a configuration, as happens with Pluto and Neptune, which are locked in a 3-to-2 resonance that has kept them from colliding for billions of years, or it can destabilize one, causing orbits to become increasingly eccentric over time. The difference between stability and chaos depends on the specific details of the resonance and the masses involved. In the early solar system, the balance was different. Conditions that led to chaos then have since settled into configurations that are broadly stable for the next several billion years. But broadly stable is not the same as permanently stable. Computer simulations of the long-term evolution of the solar system reveal something unsettling. Over timescales of billions of years, the inner solar system is not perfectly predictable. Tiny uncertainties in the current positions and velocities of the planets grow exponentially over time. The same resonances that can stabilize an orbit can, given enough time, destabilize one. The solar system's stability is probabilistic, not guaranteed. We do not live in a permanent arrangement. We live in an arrangement that has been stable for a few billion years and will likely remain stable for several billion more. That is a genuinely long time. But the solar system itself has been operating for 4.6 billion years already. In the remaining time, before the Sun exhausts its hydrogen fuel and expands to engulf the inner planets, the possibility of dramatic change remains real. Beyond Mars, the danger does not diminish. It organizes itself. To understand how the danger from the outer solar system continues to reach the inner planets today, you need to understand the asteroid belt. Between Mars and Jupiter, spanning from roughly 205 million miles to 300 million miles from the Sun, there is a region occupied by millions of rocky and metallic objects. Some are tiny, just pebbles or boulders. Others are substantial worlds. Ceres, the largest object in the asteroid belt, has a diameter of about 585 miles. It is classified as a dwarf planet. It is massive enough that gravity has pulled it into a roughly spherical shape. Vesta, the second largest, is about 329 miles across and one of the most massive objects in the belt. The total mass of all material in the asteroid belt combined is roughly 4% of the Moon's mass. That might seem modest, but that does not make the belt irrelevant, because it is not the total mass that matters. It is the number of objects, the trajectories, and what happens when those trajectories are disturbed. Jupiter's gravity is the dominant force shaping the asteroid belt. Jupiter's immense gravitational influence creates regions within the belt where the orbital resonances are unstable. Objects that drift into these regions, called Kirkwood gaps, find their orbits perturbed by Jupiter's periodic gravitational tugs. Those perturbations can kick an asteroid out of its stable orbit and send it on a new trajectory. Sometimes that trajectory leads out of the solar system. Sometimes it leads inward, toward the rocky planets, toward Earth. There is also a gentler, slower process steadily pushing some asteroids toward the inner solar system. It is called the Yarkovsky effect. When sunlight hits an asteroid, it warms the surface. As the asteroid rotates, the warmed surface eventually faces away from the Sun and radiates that heat back into space. The direction of this heat radiation depends on the asteroid's rotation, and momentum is carried by radiation. The net result is a tiny but persistent force, pushing the asteroid very gradually along its orbit. Over millions and tens of millions of years, this tiny force can shift an asteroid's orbit enough to push it into a Kirkwood gap, where Jupiter's resonances then take over and fling it onto a dramatically new trajectory. The Yarkovsky effect has been measured directly for a handful of asteroids, and it means that the asteroid population threatening Earth is not fixed. It is continuously being refreshed. New asteroids are being nudged out of stable orbits in the belt and placed onto Earth-crossing trajectories on geological timescales. The source of dangerous impactors is not a fixed, depleting reservoir. It is being restocked by physics. Near-Earth objects are asteroids and comets, whose orbits bring them into the region of space within roughly 121 million miles of the Sun. There are over 33,000 known near-Earth asteroids. Of those, over 2,300 are classified as potentially hazardous. That classification means they are larger than about 460 feet across and pass close enough to Earth's orbit to be of concern. The Chicxulub impactor, the asteroid widely accepted to have caused the mass extinction that ended the age of the dinosaurs 66 million years ago, was estimated at roughly 6 miles across. It struck what is now the Yucatan Peninsula of Mexico. The energy released was roughly 1 billion times that of the atomic bomb dropped on Hiroshima. The immediate destruction was catastrophic. But the longer-term effects were arguably worse. The impact vaporized rock and ejected enormous quantities of debris into the stratosphere. Soot from global wildfires followed. The combined effect blocked sunlight from reaching the surface for years, perhaps over a decade. Global temperatures plummeted. Photosynthesis collapsed. Food chains broke down at their base. An estimated 75% of all species on Earth went extinct. The non-avian dinosaurs, which had dominated the planet for over 160 million years, were gone. The Chicxulub event was not the only catastrophic impact in Earth's history. The geological record contains traces of others. The Vredefort Dome in South Africa is the remnant of an impact crater, roughly 186 miles across, formed about 2 billion years ago. The Sudbury Basin in Ontario is the remnant of a crater, roughly 125 miles across, formed roughly 1,850 million years ago. These are two of the largest confirmed impact structures on Earth. They are ancient. The geological processes that erase craters have been working on them for hundreds of millions or billions of years. What remains is a fraction of the original structure. The impacts that formed them were significantly more energetic than Chicxulub. Now consider that the solar system still contains millions of objects capable of similar or larger impacts. There are no near-Earth asteroids larger than a mile across. There are likely many more we have not found yet. The survey of potentially hazardous asteroids is ongoing but not complete. In 2013, a small asteroid estimated at roughly 60 feet across entered Earth's atmosphere over Chelyabinsk, Russia. It exploded at high altitude with a force equivalent to roughly 30 times the Hiroshima bomb. The shockwave shattered windows across a wide area. Roughly 1,500 people were hurt by flying glass. The object was completely undetected before entry. Nobody knew it was coming. It arrived from the direction of the Sun, where our ground-based telescopes cannot look effectively. A larger object on the same trajectory, arriving with the same lack of warning, would be a very different kind of event. And events like it happen. Not every day, not every year. But on the timescale of human civilization, they happen. The Tunguska event of 1908, The largest impact event in recorded human history was caused by an object estimated at roughly 160 to 200 feet across. It entered the atmosphere over Siberia and exploded at altitude with a force estimated at 10 to 15 megatons of TNT. No crater was formed. The object was consumed by the atmosphere. But over 800 square miles of forest were flattened by the shockwave. An estimated 80 million trees knocked down. Had the object arrived about 4 hours later, due to Earth's rotation, it would have exploded over a major population center. Nobody saw it coming. Nobody saw it at all, from any direction, in advance. It just arrived. Before leaving the inner solar system behind, one more thing. The solar system's most extreme temperature contrasts exist in places surprisingly close to each other. In permanently shadowed craters near the poles of Mercury and the Moon, temperatures can drop to roughly minus 370 degrees Fahrenheit, about minus 223 degrees Celsius. These are among the coldest naturally occurring surfaces in the solar system, colder than the surface of Pluto. The reason is simple. The sun never shines directly into these deep crater floors. The crater walls are high enough that sunlight cannot reach the bottom. The surfaces there have not seen direct sunlight in billions of years. Without sunlight, there is no heating beyond what reaches them from other sources. The temperature in these shadows approaches thermodynamic equilibrium with the cold of space. These frozen crater floors are natural cold traps. Any volatile material, water ice, carbon dioxide, methane, that lands in them stays. It does not evaporate. NASA's lunar missions found water ice in permanently shadowed craters near the lunar South Pole. Mercury's MESSENGER mission found ice in permanently shadowed craters near Mercury's poles. Ice on Mercury, the planet closest to the Sun, in permanent shadow, mere miles from surfaces hot enough to melt lead. The difference between the sunlit surface of Mercury and the permanently shadowed floor of a nearby crater is more than 1,000 degrees Fahrenheit. Across the entire solar system, the temperature range spans from millions of degrees in the solar corona to just fractions of a degree above absolute zero in permanently shadowed polar craters and in the cold depths of the Oort cloud. All of this extreme range exists within what we call our neighborhood. The current survey of potentially hazardous asteroids is ongoing. The goal is to find, before impact, any large object on a collision course. For most large objects, we now have decades of advance warning if they pose a threat. For smaller objects, the situation is more uncertain. And for objects arriving from certain directions, warning can be minimal regardless of size. The Planetary Defense Mission, DART, launched by NASA in November 2021, deliberately crashed into an asteroid called Dimorphos in September 2022. The impact measurably changed the asteroid's orbital period around its larger companion, Didymos. It was the first time humanity intentionally altered the motion of a natural body in the solar system. The kinetic impactor technique works. It requires finding the object far enough in advance to mount a mission. It requires years of lead time. It requires the resources and the will to act. All of those requirements depend on surveillance of the sky that is ongoing but not yet complete. The first generation of purpose-built planetary defense observatories is coming online. NASA's NEO-Surveyor Space Telescope, designed to find near-Earth objects that ground-based telescopes miss due to their proximity to the Sun, is in development. The Vera Rubin Observatory in Chile, a survey telescope of extraordinary capability, will systematically catalogue millions of solar system objects over the next decade. These tools represent the beginning of taking seriously what the solar system actually is. Not a peaceful backdrop, an active environment that requires monitoring and, eventually, management. A species that barely understood the solar system a century ago has now intentionally nudged an asteroid. That is worth acknowledging. Now cross the asteroid belt and leave the inner solar system behind. Jupiter, Saturn, Uranus, and Neptune are not simply large versions of Earth. They are a completely different kind of world, operating by different physics at a different scale, and with properties that challenge ordinary intuition in ways that are difficult to fully describe. Jupiter is the largest planet in the solar system, with a diameter of roughly 88,800 miles. Earth's diameter is roughly 7,917 miles. Jupiter is about 11 times wider than Earth. You could fit more than 1,300 Earths inside it. Its mass is about 318 times greater than Earth's, more than 2 times the mass of all the other planets in the solar system combined. Jupiter has no solid surface. As you descend through its atmosphere, the pressure increases until the hydrogen gas transitions into a liquid. Deeper still, the liquid hydrogen becomes metallic under pressures and temperatures so extreme that the electrons are torn away from their atoms, and the hydrogen conducts electricity like a metal. The metallic hydrogen layer is thousands of miles deep. It generates Jupiter's magnetic field, which is roughly 20,000 times stronger than Earth's. Jupiter's magnetosphere is the largest structure in the solar system by volume. If it were visible to the naked eye from Earth, it would appear in the sky roughly 5 times the width of the full moon, even though Jupiter itself is just a bright point of light. The Great Red Spot on Jupiter is a storm that has been observed continuously for at least 350 years, and almost certainly much longer. It is a high-pressure anticyclonic system rotating counterclockwise, spanning a width that at its largest historical extent was more than twice the diameter of Earth. A storm on another planet, larger than our entire world, that has been raging for centuries. Lightning occurs inside Jupiter's storms on a scale that makes Earth's thunderstorms seem trivial. The Juno spacecraft, which entered Jupiter's orbit in 2016, detected lightning strikes in Jupiter's atmosphere, discharging enormous quantities of energy. Jupiter's most powerful lightning discharges appear to be some of the most energetic in the solar system. Jupiter's 4 large Galilean moons, discovered by Galileo Galilei in 1610, are worlds in their own right. Io, the innermost, is the most volcanically active world known anywhere. It is constantly being squeezed and stretched by the competing gravitational pulls of Jupiter on one side and the other large moons on the other. This tidal flexing generates enormous internal heat. Io has hundreds of active volcanoes. Some of its volcanic plumes reach altitudes of over 300 miles above the surface. The surface is constantly being resurfaced by lava and sulfur compounds. There are no impact craters visible on Io's surface because the geological activity erases them faster than they can accumulate. Io is geologically the youngest surface in the solar system, perpetually renewed by its own volcanism. Europa, the second Galilean moon, is covered in a shell of water ice. Beneath that ice, maintained liquid by the same tidal flexing that powers Io's volcanoes, there is an ocean of liquid water. The ocean is estimated to be roughly 60 to 100 miles deep, It contains more liquid water than all of Earth's oceans combined. And it has existed in liquid form for a very long time. The surface of Europa is marked by networks of cracks, ridges, and disrupted terrain that suggest the ice shell is mobile, floating on the liquid ocean beneath, occasionally fracturing and refreezing. Scientists consider Europa one of the most promising places in the solar system to search for life beyond Earth. The ocean has liquid water, likely has chemical energy from hydrothermal activity on the ocean floor, and has been stable over geological time. Those are conditions where life has arisen on Earth. Whether it has arisen on Europa is unknown. Ganymede, the third and largest of the Galilean moons, is larger than the planet Mercury. It has its own magnetic field, the only moon in the solar system known to do so. Callisto, the outermost large moon, may also have a subsurface ocean. Its surface is the most heavily cratered of the Galilean moons. It has been hit so many times and has so little geological activity to erase old craters that its surface is essentially saturated with impacts. Every part of it has been struck many times over. Callisto's surface is a geological archive written in craters. But the danger around Jupiter is not only from the planet itself. Jupiter's magnetic field is so powerful, and so much material streams through it from Io's volcanic eruptions, that the space around Jupiter is one of the most intensely radioactive environments in the solar system. Io is constantly pumping sulfur dioxide and other volcanic material into Jupiter's magnetosphere. This material gets ionized and trapped in Jupiter's magnetic field, forming a plasma torus, a ring of charged gas surrounding Jupiter in the region of Io's orbit. The radiation in Jupiter's inner magnetosphere is intense enough to be lethal to humans within minutes of exposure without shielding. It would damage unshielded spacecraft electronics within hours to days. The Juno spacecraft, designed to orbit Jupiter and study it closely, uses a radiation-hardened titanium vault to protect its most sensitive electronics. Even with that protection, the accumulated radiation dose over the mission affected some instruments. Europa, one of the most scientifically compelling targets in the solar system, sits in the most intense part of Jupiter's radiation belts. Making a long-duration mission to Europa is one of the most technically challenging problems in planetary science. NASA's Europa Clipper mission, launched in 2024, is designed to make repeated flybys of Europa rather than orbiting it, reducing the total radiation exposure. The beautiful images of gas giant atmospheres and moon landscapes transmitted across billions of miles by hardy spacecraft give no sense of the environment surrounding those spacecraft. The environment those probes had to survive to send those images back. In July 1994, astronomers watched as comet Shoemaker-Levy 9, a comet that had been captured by Jupiter and broken apart by its tidal forces, fell into Jupiter piece by piece over 6 days. 21 large fragments, the largest estimated at about 1 mile across, struck Jupiter in sequence. Each impact left a dark scar in Jupiter's atmosphere larger than Earth. The energy released per impact was estimated at millions of megatons of TNT. This was the first time in human history that an extraterrestrial collision was predicted in advance and observed in real time. And it was the scale of destruction that registered. An object 1 mile across struck a planet the size of Jupiter, and the mark it left was larger than the entire Earth. If an object of that size had struck Earth instead of Jupiter, the consequences would have been extinction level. Jupiter does deflect some comets that might otherwise threaten the inner solar system. But it also, through gravitational interactions, can send some objects on paths toward Earth that might have remained in the outer solar system indefinitely. Jupiter's role is complicated. It is not simply a shield. It is a gravitational sculptor of everything around it. What happens at Jupiter does not stay at Jupiter. Saturn's rings are perhaps the most photographed feature of the solar system. They appear in every space documentary, every astronomy textbook, every image from telescopes large enough to resolve them. And they are genuinely beautiful. But what they actually represent is considerably more striking than beautiful. Saturn's rings are composed primarily of water, ice, and rocky debris, ranging in size from tiny grains, smaller than a grain of sand, to chunks as large as a house. The main ring system extends from about 4,200 miles to roughly 82,000 miles above Saturn's equator. The rings are extraordinarily thin relative to their width. The main rings are, in most places, between 30 feet and 300 feet thick. For context, a sheet of paper is roughly 4/1000ths of an inch thick. If you scaled the rings down so that their diameter was the width of a standard sheet of paper, the rings would be thinner than a single atom. The rings are not static. Material within them is constantly colliding, breaking apart, and clumping together. They are maintained and shaped by shepherd moons, small moons whose gravity herds the ring particles and prevents them from spreading. But the rings are also slowly disappearing. A process called ring rain pulls ring material into Saturn's upper atmosphere. NASA estimates, based on data from the Cassini mission, that Saturn's rings are being lost at a rate of up to 10,000 kilograms per second. At that rate, the rings would completely disappear in somewhere between 100 million and 300 million years. In geological terms, they will be gone soon. The rings of Saturn are not a permanent feature of the solar system. They are a temporary structure, currently visible because we happen to exist during the cosmically brief window when they are present. What the rings represent is a record of violence. They are almost certainly the remnant of a moon or a comet that was torn apart by Saturn's gravity, or a moon that was struck by an impactor large enough to shatter it. The beautiful ring system, visible through any small telescope, is, in reality, the debris field of a catastrophic ancient destruction. And Saturn is not alone in having rings. Jupiter has a faint ring system. So does Uranus. So does Neptune. Every giant planet in the outer solar system has rings. When you understand what rings are, that fact takes on a different weight. Every outer planet has at least one record of something being destroyed. Saturn's largest moon, Titan, is unlike anything else in the solar system. It has a thick nitrogen atmosphere, denser than Earth's. The atmospheric pressure at Titan's surface is about 1.5 times Earth's sea level pressure. There are methane lakes and seas on the surface. Methane rain falls from methane clouds. There is a full hydrological cycle operating, but with methane playing the role that water plays on Earth. Temperatures on the surface average around -290 degrees Fahrenheit, roughly -179 degrees Celsius. At those temperatures, methane can exist as a liquid. The Cassini-Huygens mission revealed a world with sand dunes made of organic molecules, river channels carved by methane, and vast, smooth seas of liquid methane near the poles. Titan's atmospheric chemistry is extraordinarily complex. Ultraviolet radiation from the sun drives chemical reactions in the upper atmosphere that produce a variety of organic molecules, which eventually settle to the surface. The surface of Titan is covered in organic chemistry that, on Earth, would be considered prebiotic, before life, but not unlike the chemistry from which life on Earth may have emerged. And then there is Enceladus, one of Saturn's smaller moons, only about 313 miles across. The Cassini spacecraft discovered that Enceladus has geysers at its south pole, shooting plumes of water vapor and ice particles hundreds of miles into space. Those plumes originate from a subsurface, liquid water ocean. The water is being heated by tidal forces. The Cassini spacecraft flew through these plumes and detected not just water and ice, but organic molecules and molecular hydrogen. Molecular hydrogen is produced by a specific chemical reaction between hot water and rock called serpentinization. The same reaction occurs at hydrothermal vents in Earth's deep oceans. Those hydrothermal vents on Earth are some of the most biologically rich environments on the planet. They harbor entire ecosystems that do not depend on sunlight, driven entirely by chemical energy. Enceladus appears to have the ingredients for a similar system. It has liquid water. It has organic molecules. It has a probable hydrothermal system at its ocean floor. If there is a place in the solar system where life might exist right now, today, Enceladus is near the top of any serious list. Uranus is the most geometrically strange major planet in the solar system. It orbits the Sun essentially on its side, with an axial tilt of about 97.8 degrees. Earth's axial tilt is roughly 23.4 degrees, which gives us our seasons. Uranus's tilt is so extreme that during the course of its roughly 84-year orbit, each pole points almost directly at the Sun for about 21 years, then spends 21 years in complete darkness. The seasons on Uranus are unlike anything in the inner solar system. The most accepted explanation for this tilt is that Uranus was struck by a large object, possibly several times the mass of Earth, during the early history of the solar system. The impact was energetic enough to tip the entire planet onto its side. That impact also produced Uranus's ring system and its collection of moons. Uranus is, in this sense, a monument to an impact we cannot directly study. We can only see its aftermath in the geometry of how the planet currently moves. Neptune, the final planet, is a world of supersonic storms. Wind speeds on Neptune have been measured at roughly 1,200 miles per hour. That is about 1.5 times the speed of sound in Earth's atmosphere. The cause of these winds is not fully understood. Neptune receives very little energy from the Sun, being so far away, yet it has more vigorous atmospheric dynamics than Uranus, which is actually closer to the Sun. The planet radiates roughly 2.5 times as much energy as it receives from the Sun. There is an internal heat source, almost certainly left over from the planet's formation, that has not cooled off in 4.5 billion years. Models suggest that at sufficient depths within Neptune, the pressure may cause carbon to form diamonds, which would slowly rain down through the interior toward the core. Diamond rain. On a planet nearly 2,800 million miles from the Sun. This is not science fiction. It is the prediction of current planetary science, supported by experiments recreating extreme pressure conditions in laboratories on Earth. The outer solar system contains worlds operating under conditions that have no analog in human experience. Beyond Neptune, the solar system does not end. For much of the 20th century, the solar system was thought to consist of the Sun, the 8 planets, their moons, the asteroid belt, and some comets. That picture began to fall apart in 1992 when astronomers David Jewitt and Jane Liu discovered the first confirmed Kuiper Belt object beyond Pluto. Since then, thousands more have been found. The Kuiper Belt is an enormous disk of icy bodies, stretching from Neptune's orbit outward to about 50 astronomical units. It contains hundreds of thousands of objects larger than about 60 miles across, and millions of smaller ones. The largest Kuiper Belt objects are substantial worlds. Pluto, once the 9th planet, has a diameter of roughly 1,477 miles. Eris, discovered in 2005, is slightly smaller than Pluto, but more massive. Makemake and Haumea are also substantial bodies. Haumea is so rapidly rotating that it has been deformed into an egg shape, flattened at the poles and extended at the equator. Its day is only about 4 hours long. It has 2 moons and a ring system, discovered in 2017, a ring system around a potato-shaped icy world in the far outer solar system. The solar system, even in its quieter outer reaches, continues to produce surprises. These worlds are not simply peaceful, frozen relics. They are dynamically active members of the solar system, subject to gravitational interactions with Neptune that can alter their orbits over millions of years. Occasionally, an object from the Kuiper Belt gets nudged into a new trajectory. It falls inward toward the Sun. As it approaches and heats up, volatile ices on its surface sublimate, releasing gas and dust. It grows a coma, a temporary atmosphere, and a tail. It becomes a comet. Short-period comets, those with orbital periods of less than 200 years, are generally thought to originate in the Kuiper Belt. The Kuiper Belt is also not a static reservoir. It is continuously shedding material inward, and the objects doing that shedding have a name. Then there are the centaurs. Most people have never heard of them, but they represent one of the more unsettling populations of objects in the solar system. Centaurs are bodies that orbit in the outer solar system, primarily between Jupiter and Neptune, but their orbits are gravitationally unstable. They are transitional objects. They have not settled into stable long-term orbits. They are in the process of being moved. Many centaurs began as Kuiper Belt objects and were scattered inward by gravitational interactions with Neptune. They now exist in a kind of orbital limbo, crossing the orbits of the outer planets, subject to gravitational perturbations from Jupiter, Saturn, Uranus, and Neptune, being nudged and pulled and eventually sorted into a new trajectory. Some of them will ultimately be ejected from the solar system. Some will fall into the Sun, and some will be deflected inward into the inner solar system, where they will become comets. The timescale for this process is millions of years. The centaur population is not a static collection of objects, but a continuous flow of material from the Kuiper Belt into the inner solar system. A significant centaur, large enough to qualify as a minor planet, is Chiron, which was the first centaur discovered, identified in 1977. Chiron is roughly 150 miles across. It occasionally shows cometary activity, producing a faint coma when it is closer to the Sun. It is not currently on a trajectory that threatens Earth. But it is a reminder that the reservoir of potentially dangerous objects in the outer solar system is not stationary. It is draining, slowly, inward. The Kuiper belt is continuously losing objects to Neptune's gravitational influence. Those objects travel inward. Some become short-period comets that we can track and catalogue. Others pass through the inner solar system and are ejected or destroyed before we have any record of them. The populations of objects in the solar system are not fixed inventories. They are dynamic, flowing, constantly being redistributed. And the flow, on the whole, is from the outer solar system inward, toward us. The space between the planets is not a perfect vacuum. It is filled with a thin cloud of dust particles, released by comets as they evaporate near the Sun, and created by collisions among asteroids and Kuiper belt objects. This dust forms a flattened disk aligned with the plane of the solar system. From Earth, this disk is occasionally visible, on very dark, clear nights, as a faint pyramid of light along the ecliptic just after sunset or just before sunrise. It is called the zodiacal light. The particles in this cloud are being continuously swept up by the planets, blown away by solar radiation pressure, and replenished by new sources. Earth accumulates roughly 40,000 tons of extraterrestrial dust every year. Most of it is invisible, just tiny particles settling through the atmosphere. Some arrives as micrometeorites, tiny spherical droplets formed when small particles are heated to melting by atmospheric entry. These micrometeorites contain information about the outer solar system that no spacecraft has yet visited. They are samples of comets and asteroids, delivered to Earth's surface for free. Scientists collect them from Antarctic ice cores and high-altitude air samples, where they can be isolated from terrestrial contamination. The dust fills every part of the solar system. It scatters sunlight. It carries information. It connects every part of the system to every other part in a subtle, constant flow of material. The solar system is not a collection of isolated bodies. It is a connected system of ongoing material exchange. Dust flows from comets to planets. Asteroid fragments from collisions drift through the belt and eventually fall into the Sun or onto planetary surfaces. Comets shed material on every pass through the inner solar system, and that material lingers for millions of years. When Earth passes through the debris trail of an old comet, we experience a meteor shower. The Perseids, one of the most reliable annual meteor showers, come from the debris trail of comet Swift-Tuttle. Swift-Tuttle is a comet about 16 miles across. It last passed through the inner solar system in 1992. Its debris trail, the source of the Perseids, has been accumulating for thousands of years. Every August, Earth plows through it. Every August, material that was once part of a comet nucleus, shed when that nucleus passed close to the Sun, ends its journey by burning up in Earth's atmosphere. Beyond the Kuiper belt begins the region that is perhaps the most arresting of all when you absorb what it actually means: the Oort cloud. If the Kuiper belt is the outer suburbs of the solar system, the Oort cloud is the wilderness. It is thought to extend from about 2,000 astronomical units all the way out to somewhere between 50,000 and 100,000 astronomical units from the Sun. At the inner edge of the Oort cloud, you are already roughly 186 billion miles from the Sun. At the outer edge, you are approaching the gravitational midpoint between our Sun and the nearest other stars. The Oort cloud is not flat like the Kuiper belt. It is a roughly spherical shell surrounding the entire solar system in every direction. It contains an estimated 2 trillion or more icy objects. 2 trillion. At those distances, the Sun is just the brightest star in the sky. Temperatures hover near absolute zero. These objects orbit so slowly and so far out that a single orbit can take millions of years to complete. And occasionally, the gravitational influence of a passing star, or a molecular cloud, or the galactic tidal forces arising from the structure of the Milky Way itself, perturbs an Oort cloud object. Its orbit shifts. It begins to fall inward. It falls for millions of years. Finally, it arrives in the inner solar system as a long-period comet, a visitor from the deepest darkness of the solar system. These long-period comets are among the most hazardous objects in the solar system because they are essentially undetectable until they arrive. They have never been heated by the sun before, so they can be extraordinarily bright and active as they fall inward. And we may have only months of warning before they reach the inner solar system. The galactic tidal force causing these orbital perturbations is not random or occasional. It is constant. The Sun is orbiting the center of the Milky Way at roughly 514,000 miles per hour. That orbit carries the entire solar system through different regions of the galaxy over millions of years. As the solar system moves, the galactic tidal forces on the Oort cloud change. The solar system also oscillates above and below the galactic plane as it orbits the galaxy center on a cycle of roughly 30 to 35 million years. During parts of this cycle, the solar system passes through denser regions of the galactic disk. The tidal forces on the Oort cloud are enhanced. More objects are perturbed. More comets fall inward. Some researchers have proposed that mass extinctions in Earth's geological record show a rough periodicity that might match this galactic oscillation. The evidence remains controversial, but the underlying mechanism is real. The galaxy itself reaches in and stirs the outer solar system. Our home is not insulated from the larger cosmos around it. It is embedded in it, and the stars themselves occasionally contribute directly. Close stellar encounters, events where another star passes within a few light years of the Sun, occur on timescales of tens of millions of years. When a star passes close, its gravity can significantly perturb the Oort cloud, sending showers of comets toward the inner solar system. In 2014, astronomers identified a red dwarf star called Schultz's star that passed within about 0.8 light-years of the Sun roughly 70,000 years ago. That is well within the outer Oort cloud. The encounter was too brief and too slow to trigger an immediate flood of comets in the inner solar system, but it would have perturbed many Oort cloud orbits. Effects of that perturbation may still be working their way inward today. Stars passing even closer would have more dramatic consequences, and in the lifetime of the solar system, such encounters have certainly occurred. The Oort cloud has been stirred repeatedly. What we see incoming from the outer darkness is the accumulated result of billions of years of gravitational disturbances. In 2017, astronomers detected an object passing through the solar system that had come from outside it entirely, an interstellar visitor. It was called Oumuamua, a Hawaiian name meaning something like the first distant messenger from long ago. Oumuamua was unlike any solar system object ever seen. It was highly elongated in shape, possibly a disc or cigar shape, tens of times longer than it was wide. It was tumbling as it traveled. It accelerated as it left the solar system in a way that could not be explained by gravity alone. The best current explanation is that it was being pushed by radiation pressure like a solar sail. But its composition, its origin, its exact shape, and the cause of its excess acceleration remain subjects of scientific debate. In 2019, a second interstellar object was detected passing through the solar system. This one, called Borisov, was clearly a comet, shedding material as it passed close to the Sun. Borisov appeared to be compositionally similar to comets from our own solar system, suggesting that some comets from other planetary systems may be broadly similar to ours. The detection of these interstellar visitors revealed something important. The space between stellar systems is not entirely empty. Objects from other planetary systems, flung out by the gravitational dynamics of those systems, travel through interstellar space and occasionally pass through the solar system. It is a reminder that the solar system is not a sealed environment. It is a porous one. Objects can enter from outside. And objects from the solar system have presumably been flung into interstellar space, crossing the void between stars. The solar system, for all its vast extent, is not the whole story. There is a hypothesis that has circulated among planetary scientists for years, and it refuses to go away. It is called Planet 9. And if it exists, it changes our picture of the outer solar system in a fundamental way. The evidence is indirect. In the Kuiper belt, beyond Neptune, there is a handful of extreme trans-Neptunian objects whose orbits are clustered in a way that seems statistically improbable. Their orbits are not randomly distributed, as you would expect if nothing were influencing them. They appear to be shepherded, organized, nudged into a common alignment by the gravitational influence of something massive that we have not yet found. The calculations suggest that the unseen object, if it exists, is a planet roughly 5 to 10 times the mass of Earth. It would orbit at an extraordinary distance, somewhere between 400 and 800 astronomical units from the Sun. That is 4 to 8 times farther from the Sun than Neptune. Its orbital period would be somewhere between 10,000 and 20,000 years. It has never completed a single orbit in the entire span of recorded human history. Not even close. At that distance, it would be extraordinarily faint, reflecting almost no light, making it essentially invisible to current observational surveys. We would need a very large telescope looking in exactly the right part of the sky to have any chance of finding it. What is Planet 9? One hypothesis is that it is a planet that formed in the inner solar system during the early chaotic period and was ejected outward by gravitational interactions with Jupiter or Saturn. Another is that it is a captured rogue planet, a world that formed around another star and was gravitationally snagged by the Sun during the early period when the Sun was still embedded in its birth cluster. A third possibility is that it does not exist at all, and the clustering of trans-Neptunian objects is a statistical artifact produced by observational bias. We look at more of the sky in some directions than others, and that could create the appearance of clustering where none actually exists. This is the current state of the science. We do not know. But the fact that we are seriously discussing the possibility that a planet 5 to 10 times the mass of Earth exists in our own solar system, in a region we have only barely begun to survey, says something profound about how little of this neighborhood we have actually seen. We have been doing astronomy for thousands of years. We have been doing sophisticated telescope-based astronomy for roughly 400 years. We have been doing spacecraft-based exploration for about 70 years. And there may be a world larger than Earth orbiting in our own solar system that we have simply never noticed. The solar system has not finished revealing itself. We are still discovering it. Now step back from the solar system itself, entirely from every planet, every moon, every comet and asteroid, and look at where all of it actually sits. The Sun, and every planet orbiting it, is moving through the Milky Way at roughly 514,000 miles per hour. The Sun takes roughly 225 to 250 million years to complete one orbit around the galactic center. Earth has completed roughly 20 galactic years in its existence. As the solar system moves through the galaxy, it passes through different regions with different stellar densities, different molecular cloud distributions, different gravitational environments. These changes have shaped the history of life on this planet in ways we do not fully understand. The solar system is not a closed system operating in isolation. It is a participant in the larger structure of the Milky Way. And the solar system, through the material it has shed into interstellar space over billions of years, has contributed to the galaxy in return. Every comet that has been ejected from the solar system is now an interstellar traveler. The solar system's history is written partly in the objects that left it. The picture that emerges from all of this is not one that fits comfortably into school diagrams. It is a picture of a system that formed in chaos, settled into a relatively calm period, and remains embedded in processes that operate over timescales from seconds to billions of years. From the 8-minute journey of a solar flare's radiation to Earth, to the millions of years it takes for a comet to fall from the Oort cloud. From the 11-year solar activity cycle to the billions of years it took Mars to lose its atmosphere. The solar system is active on every timescale. On the timescale of milliseconds, lightning discharges in Jupiter's clouds. On the timescale of hours, solar flares erupt and propagate across the solar system. On the timescale of years, Jupiter's gravity nudges asteroid trajectories. On the timescale of thousands of years, comets complete inner solar system passages. On the timescale of millions of years, passing stars perturb the Oort cloud. On the timescale of tens of millions of years, the solar system oscillates above and below the galactic plane. On the timescale of hundreds of millions of years, giant planet resonances can shift the dynamics of the inner solar system. On the timescale of billions of years, the sun brightens, planets lose atmospheres, and the entire architecture of the system evolves. We happen to be alive during a relatively quiet interval in that history. Relative to the bombardment, relative to the period of orbital chaos, relative to what will happen when the sun eventually becomes a red giant and expands toward the inner planets. Our current era is a mild one. But mild is not the same as safe, and quiet is not the same as permanent. The meteorites that land on Earth carry this entire history within them, not in memory, in chemistry. Every day, roughly 100 tons of extraterrestrial material falls on Earth. Most of it is fine dust. Micrometeorites so small they float gently through the stratosphere and eventually settle to the ground without incident. But the rocky material that reaches the surface in identifiable pieces carries within it some of the most extraordinary scientific data available to us. The most primitive meteorites, the carbonaceous chondrites, are largely unmodified samples of the material from which the solar system formed 4.6 billion years ago. They contain grains that predate the solar system itself, pre-solar grains that formed in the atmospheres of stars that existed before the sun. Some of these pre-solar grains are tiny diamonds that formed around ancient carbon stars. Others are silicon carbide grains from asymptotic giant branch stars. These are physical samples of material from stars that died before our sun was born. They survived the formation of the solar system, the accretion of the rocky bodies, billions of years of existence as part of asteroids, and eventually delivery to Earth. And they are sitting in laboratories, right now, on this planet, available for analysis. The meteorite record also preserves evidence of the solar system's early violence in a direct and physical way. Some meteorites show evidence of rapid heating and cooling, consistent with impact events on their parent bodies during the period of heavy bombardment. Others show evidence of aqueous alteration, contact with liquid water, indicating that even in the early solar system, before any planets had fully formed, some small bodies were warm enough internally from radioactive decay to have liquid water in their interiors. The solar system's history is not only written in the motions of planets and the craters on surfaces. It is written in the mineralogy and chemistry of rocks that have fallen out of the sky. Rocks that are, in some cases, older than Earth. Older than any surface we can directly sample in the solar system. Older than the Moon. The meteorite record tells us that the solar system's early period was extraordinarily violent, extraordinarily energetic, and extraordinarily complex. And pieces of that record are landing on Earth right now, tonight, while you are watching this. Small fragments of ancient solar system material are settling through the atmosphere and reaching the ground. We share our planet with visitors from the beginning of time. There is one more dimension to the solar system's history that operates almost entirely invisibly. The solar system formed from a molecular cloud that was itself the product of previous stellar generations. The heavy elements in the solar system, every atom heavier than helium, was created in a star that lived and ended before the sun formed. Carbon, oxygen, nitrogen, silicon, iron, gold, uranium. All of it was forged in stellar furnaces and scattered into space when those stars ended their lives. The molecular cloud from which the sun formed contained this material. The shock wave from a nearby supernova may have triggered the collapse of the molecular cloud that formed the solar system. The isotopic ratios in the most ancient meteorites, the carbonaceous chondrites, preserve a record of the material from which the solar system formed. Anomalies in those ratios point to the contribution of material from a nearby supernova, or possibly from an evolved star that produces heavy elements in its outer layers. Whatever the precise source, the solar system began as recycled stellar material. Atoms with a history. Atoms that have been inside stars before they were part of this solar system. The iron in Earth's core has been through a stellar interior. The calcium in your bones was forged in a star. The oxygen you breathe was created by a star that ended its life before the sun began. The solar system is not just a structure in space. It is a chapter in an ongoing story. A story of matter cycling through stars, being transformed, scattered, gathered again, reformed into new structures. The violence of the solar system's past, the violence of its present, and the violence of its eventual future are all part of the same continuous process. Stars forming. Stars living. Stars ending. New stars forming from the remnants. Our solar system is a single iteration in that process, one that has lasted 4.6 billion years. One that has, in those 4.6 billion years, produced something remarkable. The search for life in the solar system has, in recent decades, expanded far beyond the original focus on Mars. And what that expansion reveals is a solar system that is, in many of its most extreme environments, potentially hospitable to life in forms we have not yet encountered. The discovery of hydrothermal vents on Earth's deep ocean floor in 1977 was a revelation. Before that discovery, it was assumed that life depended on sunlight. The hydrothermal vent communities changed that understanding completely. Entire ecosystems were found thriving in complete darkness, at depths where no sunlight could penetrate, sustained entirely by chemical energy. If life on Earth can exist in these conditions, life might exist anywhere in the solar system where liquid water and chemical energy coexist. That possibility now applies to multiple locations. Europa has a liquid water ocean and a probable hydrothermal floor. Enceladus has liquid water, organic molecules, and hydrogen produced by water-rock reactions. Titan has liquid methane, complex organic chemistry, and an atmosphere rich in the building blocks of biochemistry. The solar system that once seemed to consist of one inhabited world, surrounded by lifeless rocks and gas, has revealed itself to be something far more interesting. A system containing multiple environments where the basic conditions for life may be met. We do not know if life is present in any of these places. We have not found it. But we have not really looked. Not with the tools and access that would be required to make a meaningful search. The question of whether the solar system contains life beyond Earth is genuinely open. It is not a question of faith or speculation. It is an empirical question that we do not yet have the data to answer. And the solar system, for all its hostility, for all its violence and extremity, may turn out to contain life we have not yet found. That possibility sits quietly within all the terror and extremity. Hidden in the frozen oceans of moons, most people could not identify on a diagram, waiting for us to arrive and look. There is also the matter of what we have learned from observing other solar systems. The exoplanet revolution, which began in 1995 with the first confirmed detection of a planet orbiting a sun-like star, has revealed that planetary systems are common throughout the galaxy. Nearly every star appears to have planets. Many have systems that look nothing like ours. Hot Jupiters, gas giants orbiting so close to their stars that their year is measured in days. Systems where multiple super-Earths orbit in tight configurations. Systems with giant planets on highly eccentric orbits, sweeping through the habitable zone and disrupting any smaller planets that might otherwise form there. In comparison, our solar system appears to be relatively well-ordered. Our gas giants orbit far from the Sun in nearly circular paths. They do not sweep through the inner solar system. This configuration may have been important for allowing Earth-like planets to form and survive in stable orbits. Whether our solar system is unusual among planetary systems, or merely one of many configurations that allow complex life, is a question that remains open. We have only one example of a solar system containing life. What we can say is that our solar system has the features that allowed, in at least one instance, for the development of a technologically capable species. For now, we are here, in this solar system, in this moment, with the understanding we have managed to build. But here is what the exoplanet data has taught us that is genuinely sobering. Many of the planetary systems we observe are chaotic in ways that would preclude stable, long-term, habitable conditions. Stars with highly eccentric, giant planets appear to be the norm rather than the exception in some stellar populations. A giant planet on an eccentric orbit sweeping through the inner solar system every few years would bombard any rocky planet mercilessly. It would strip away atmospheres, redirect asteroids and comets into crossing orbits, and destabilize any carefully balanced climate system that might otherwise develop. Earth has not had to contend with this. Jupiter's nearly circular orbit keeps it in the outer solar system, acting as a partial shield rather than a perpetual aggressor. The degree to which Jupiter protects Earth by gravitationally deflecting long-period comets that might otherwise fall inward is debated. Some studies suggest Jupiter deflects roughly as many comets toward Earth as it deflects away. But its circular orbit means it does not itself become a gravitational wrecking ball passing through the inner solar system on every pass. That stability, that particular architectural feature of our solar system, may be one of the reasons a rocky planet at 93 million miles from the Sun had enough time and enough orbital peace to develop complex life. 4 billion years is a long time. Complex life required most of that time. A different giant planet configuration, a Jupiter on a highly elliptical orbit, might have meant relentless bombardment of the inner solar system. Atmospheres stripped. Surfaces sterilized. No time to develop the chemistry that eventually produced everything alive on this planet. The architecture of the solar system is not incidental to the story of life on Earth. It may be the story. And we are only beginning to understand how the particular arrangement of the planets around this particular star created the conditions that made this particular outcome possible. The Sun's life story is also worth understanding in full because it frames everything else. Stars like the Sun form from clouds of gas and dust, pulled together by gravity over millions of years. The Sun formed roughly 4.6 billion years ago from a collapsing molecular cloud. As the cloud collapsed, it heated. Eventually, the core became hot and dense enough for hydrogen fusion to begin. The Sun ignited. The outward pressure from fusion balanced the inward pull of gravity. The Sun settled into what astronomers call the main sequence, the long, stable phase of hydrogen burning that it is still in today. Main sequence stars of the Sun's mass burn for roughly 10 billion years. The Sun is about 4.6 billion years into that 10 billion year lifespan. It is middle-aged. In roughly 5 billion years, the hydrogen in the core will run out. The core will contract. The outer layers will expand dramatically. The Sun will become a red giant, swelling to perhaps 100 to 200 times its current size. The inner planets will be affected. Mercury will certainly be engulfed. Venus likely as well. What happens to Earth depends on the details of how much mass the Sun loses during this expansion and how far Earth's orbit moves outward as a result. Some models suggest Earth might migrate far enough outward to survive the red giant phase as a burned, desiccated rock. Others suggest it will be engulfed. Either way, life on Earth will have ended long before then. The oceans will boil away in roughly 1 billion years as the Sun gradually brightens. Complex life as we know it has perhaps 500 million to 1 billion years remaining. After the red giant phase, the outer layers of the Sun will be expelled as a planetary nebula. The core will remain as a dense, hot, white dwarf. A sphere roughly the size of Earth, but containing the mass of the Sun, slowly cooling over billions of years. The solar system, if it survives the red giant phase in any form, will orbit a white dwarf for longer than the current age of the universe. This is not a distant possibility. It is a certain future. The Sun's evolution is the clock against which all of life on Earth is ultimately measured, and it is ticking. What makes this more immediate than it sounds is the gradual brightening of the sun that is happening right now. Every 100 million years or so, the sun's luminosity increases by a fraction of a percent. That sounds trivial. Over geological time, it is not. The geological record of Earth's climate contains evidence of a planet that has managed, through various feedback mechanisms, to maintain habitable temperatures even as the sun slowly brightened. The carbon cycle, driven by plate tectonics, has played a major role. When the climate warms, chemical weathering of rocks accelerates, drawing carbon dioxide out of the atmosphere, cooling the climate. When the climate cools, weathering slows, carbon dioxide builds up from volcanic emissions, warming the climate. This negative feedback system has helped regulate Earth's temperature over hundreds of millions of years. But it is not infinitely robust. As the sun continues to brighten, the temperature increase will eventually outpace what the carbon cycle can compensate for. The feedback will fail. The oceans will warm and eventually evaporate. Water vapor will reach the upper atmosphere, where ultraviolet radiation from the sun will split the water molecules. The hydrogen will escape to space. The oxygen will react with surface rocks. The oceans will not return. Earth will become more like Venus. Not through any catastrophe, not through any dramatic singular event, simply through the sun doing what stars of its type do, slowly and inevitably getting brighter. There is one more thing worth understanding before we arrive at what all of this means. The solar system is not just physically extreme, it is temporally extreme. The timescales over which these processes operate are so vast that they challenge the human capacity to hold them in mind. And within those vast timescales, the orbital dynamics of the planets are not as stable as they appear. Numerical simulations of the solar system's orbital evolution over billions of years reveal something that should give pause. The inner solar system is not guaranteed to remain stable indefinitely. Mercury's orbit, already the most eccentric of the planets, is influenced by gravitational resonances with Jupiter. Over timescales of billions of years, those resonances can drive Mercury's eccentricity higher and higher. In roughly 1% of simulations of the solar system's long-term evolution, Mercury's orbit becomes so eccentric that it eventually collides with Venus, or falls into the Sun, or is ejected from the solar system entirely. In some of those same simulations, the gravitational disruption of Mercury's departure is enough to throw Venus and Earth into unstable configurations. Collisions between inner planets. Planetary ejections. The dissolution of the inner solar system. These are not science fiction scenarios. They are outcomes that appear in legitimate orbital simulations. The probability over the next 5 billion years, the remaining lifetime of the Sun, is low, but not zero. Most likely, the solar system will continue in its current configuration until the Sun ends its life. But most likely is not, certainly. And the mechanism for catastrophe, a slow gravitational resonance building over billions of years, is already operating. It has been operating since the planets formed. The numbers are running. We just cannot see them. There is something deeply strange about knowing you live inside a system that is, on long enough timescales, chaotic. Not chaotic in everyday experience. Not chaotic on human timescales. Not even chaotic on civilizational timescales. But chaotic in the mathematical sense that its exact long-term state is not predictable from its current state. The same equations of gravity that allow us to predict exactly where Mars will be in its orbit, tomorrow or next year or in a century, fail us when we push the simulation out far enough. Tiny uncertainties in the initial conditions grow. Different simulations with slightly different starting values diverge. The system that appears so ordered and permanent from our vantage point is, in the deep time of physics, something else entirely. It is a system balanced near stability. Near, but not at. And near stability, over billions of years, means something different than we usually allow ourselves to understand. It means this arrangement is temporary. Everything about the solar system we observe today, the positions of the planets, the configuration of the outer belt, the stability of the inner system, is a snapshot of a continuously evolving system, one that has been evolving for 4.6 billion years, one that will continue to evolve, one that will eventually look nothing like this. We happen to exist in the snapshot we know. We happen to have developed the ability to understand it. And we happen to have arrived at this understanding late enough that we can see how the snapshot fits into the larger story. That is, if you think about it, rather extraordinary. And rather strange. What, then, should we take from all of this? Not despair. Not even anxiety. What the full picture of the solar system demands is honesty. The solar system is not a comfortable place, made safe by its scale and familiar appearance. It is a dynamic, violent, extreme environment. It contains a thermonuclear star that continuously bombards everything with radiation and energetic particles. It contains billions of rocky and icy objects, many on orbits that cross or approach Earth's, capable of impacts ranging from regional disasters to mass extinctions. Its history includes periods of orbital chaos that sent the inner solar system into a bombardment lasting hundreds of millions of years. It contains gas giants operating under conditions incompatible with any life or material we know. Its outer reaches extend to within reach of the interstellar medium, where the gravitational influence of passing stars and the structure of the galaxy itself can disturb the outermost objects and send them falling inward. And it contains two neighboring planets that remind us, with absolute clarity, how narrow and contingent the conditions for a world like Earth actually are. None of this is cause for paralysis. It is cause for a clearer view. Because within all of this violence and extremity, a rocky planet at 93 million miles from a middle-aged star found itself with the right combination of factors to produce something extraordinary. Liquid water on the surface. A stable climate over geological time. A magnetic field holding back the solar wind. A moon stabilizing the axial tilt. Plate tectonics regulating the long-term chemistry of the atmosphere. And eventually, life. That life has now become intelligent enough to understand the environment it lives in, to map the asteroids, to study the sun's activity, to send spacecraft to every planet, to detect incoming objects, and to begin, carefully and deliberately, to think about what to do if one is headed our way. The solar system is terrifying, not because it is malevolent. It does not intend anything. It operates by physics, gravity, thermodynamics, orbital mechanics, nuclear physics. The laws of the universe playing out over billions of years and across billions of miles. The consequences of those laws are extreme, and we are embedded in the middle of all of it. On our planet, with its magnetic bubble and its ocean of air and its thin layer of life. separated from the full hostility of the environment by a combination of distance, geology, chemistry, and the particular fortune of being in the right place at a rare moment. Every time a solar flare erupts and Earth's magnetic field deflects the energetic particles, every time an asteroid crosses Earth's orbit but passes at a safe distance, every time a comet falls toward the Sun and burns away without reaching us, the solar system demonstrates what it actually is. And what it actually is extraordinary, not friendly, not designed for us, but extraordinary, ancient, violent, complex, and in that complexity, somehow giving rise to everything we know. The planets, the moons, the asteroids and comets, and the long, slow gravitational dance of billions of objects around a star. And, on one small rocky world, third from the Sun, at the right distance, in the right era of the right star's life, something that can look out at all of it, understand it, and feel appropriate awe. That is where we are tonight, inside the most violent neighborhood you will ever call home, looking out through billions of miles of emptiness and extremity, and finding it, despite everything, astonishing. Good night.